Hello guys, welcome back to my channel and welcome back to another video. And in this video, I would like to do a particular integral using complex analysis. And this is going to be a way more revised version of complex analysis because I think the first one that I did was quite short and there was one small error in that in terms of inequalities. So I hope I can provide you with a way more advised and revised understanding of the concept of residue theorem and contour integration. So let's get started. So we start with a problem integral, let's call it I, which is defined as the integral from 0 to infinity of the natural log of x divided by square root of x times x plus 1 squared dx. So now if you are used to dealing with the square roots, the classic technique is to get rid of the square root by this substitution. So you let u squared equals x such that when you take the root of x, the root of u squared is just u. So you have just a linear term in the place of this square root. And then you find dx, which is nothing but 2u du. And the upper and lower bounds are unchanged, so that's great. We have the integral from 0 to infinity of natural log of, in place of x we have u squared, so u squared divided by square root of x is nothing but u, and x is u squared plus 1 but the whole thing squared, dx is 2u du. The great part is the u's will cancel out and we have 2 times integral from 0 to infinity of natural log of u squared divided by u squared plus 1 the whole thing squared du. And now in case you are hoping that I would use this property of say log of a to the power b is equal to b times log of a, I'm not going to use this because if I do that I'll just have a u and then I lose the property of this integral to be symmetric about the y-axis, so because now having a u squared inside the natural log and in the denominator makes the entire integrand an even function, and I would lose that even nature if I were to take the 2 down. It would make things slightly more complicated. So since it's an even function, this means integral from 0 to infinity is same as integral from minus infinity to 0. So on the entire negative x-axis, natural log of u squared divided by u squared plus 1 the whole thing squared d. You can check this using substitution where you take u equals say negative a different variable or something, and then we retain the 2. Fine, let's add both of them. Both of these are I, so let's add them. I plus I is 2i is equal to 2 times integral from negative infinity to 0 of natural log of u squared divided by u squared plus 1 the whole thing squared du plus 2 times the integral from 0 to infinity of natural log of u squared divided by u squared plus 1 the whole thing squared du. And now we can club them together by the linearity of the integral to have 2 times integral from minus infinity to infinity of natural log of u squared divided by u squared plus 1 the whole thing squared du, and that's 2i. So you can cancel the 2's out. We have I is equal to integral from negative to positive infinity of natural log of u squared divided by u squared plus 1 the whole thing squared du. And that's really useful because now we have integral going from negative infinity to positive infinity, and that's helpful when it comes to designing our contour, because After this, we're going to go complex. We're going to use complex analysis, residue theorem, and the associated contour integration. So having an integral from minus infinity to infinity is extremely beneficial if we are to have the contour that we desire, you know, which in this case is a semicircle. And I'll give you a brief insight how to choose contours on the next page. See you there. So this was basically our integral, right? Our original I. Now let's make it complex because we're going to perform complex analysis. We need a complex variable, not a simple variable such as not a real variable. So let's convert everything to z. So f of z or z, I just interchange between the two pronunciations, so excuse me if I do that, can be defined as natural log of z squared divided by z squared plus 1 the whole thing squared. That's f of z. So what we have here, the complex version of this, is basically integral from minus infinity to infinity of f of z dz. Okay, that's the complex variable, and by convention z is x plus iy, because z is basically a complex variable. X is the real part, y is the imaginary part. That's the basic fact about complex numbers you ought to know. Now it's actually time to draw our contour. So let's do that. So that's basically what a contour is going to look like, and this, in the ideal case, is a perfect semicircle. But I can't do it. I'm a really bad artist. So excuse me if you have problems with that. So this is the real axis, and this point is what I'm going to call negative r, and this point is what I'm going to call r. And this entire semicircular path, this upper arc, is what I'm going to call gamma. So we are going to go from minus r to r, and then we're going to arc back this way to minus r again. So it's a closed loop essentially. And for all our cases, it need not be a closed loop. I forgot to draw the imaginary axis. It need not be a closed loop always, because that totally depends on the denominator. If the denominator is something like, say, u cubed plus 1, then over here we have subtended an angle. The final angle is 180 degrees or pi radians. One general intuition that you can develop is to subtend an angle of 2 pi over whatever this power is, in this case 3. So 2 pi over 3, that will be 120 degrees. It will be something like this. So if it's 4, then 2 pi over 2, which will 2 pi over 4, sorry, which will be pi over 2, or an angle of 90 degrees, because that will help to simplify things a lot. So that's one intuition that you can develop to while constructing these contours. So if you have an expression like u to the n plus 1 in the denominator, then the final angle that the contour will subtend from 0 is 2 pi over n. This may not be true for all cases, but it's a helpful thing to try out this before anything else. Now, having drawn the contour, it's actually time to write our contour equation. So the contour integral of our function f of z dz, obviously, or the entire thing, is, you can write it in pieces. So first piece is going from minus r to r. So integral from minus r to r of f of z dz plus, and then when you're basically arcing back, that's path gamma, integral over gamma of f of z dz. So that is essentially our contour equation, and this part, integral from minus r to r, in a limit, we are going to make it look like our I that we started with. So if you want, I can just rewrite everything. So the contour integral is going to be integral from minus r to r of, this is going to be f of x dx, because notice that the part of minus r to r is on the real axis, right? So on the real axis, if you had a complex variable z equals x plus iy, there is no imaginary part y, so this is just 0, so z is equal to x. That's why we have this. Plus integral over gamma of f of z dz. Now let's consider this integral over gamma on a fresh page, and we'll consider it in a section that's called the estimation lemma. So we have to consider this integral over gamma of f of z dz. Now let's make a substitution for f of z. We have integral over gamma of natural log of z squared, actually 2 is inside the argument, divided by z squared plus 1 the whole thing squared dz. And just for this estimation lemma, I would like to bring the 2 down and multiply it with the entire expression. So we have 2 times integral over gamma of natural log of z over z squared plus 1 the whole thing squared dz. So the way the estimation lemma works is you take the absolute value of this entire expression. So you take, more than calling it an absolute value, you can say it's the mod, because we're dealing with complex numbers. There's a slight difference between absolute values and mods. So the mod of this expression 2 times integral over gamma of natural log of z over z squared plus 1 the whole thing squared dz. And you can take the 2 out of this mod, because 2 is just a scalar. It doesn't matter if you multiply it inside or outside. This is going to be the mod of integral over gamma of natural log of z divided by z squared plus 1 the whole thing squared dz within mods. And now by this one inequality, this is less than or equal to 2 as it is, integral over gamma of, now take the mod inside. So there is this inequality. So mod of an integral is less than integral of the mod. So natural log of z over z squared plus 1 the whole thing squared dz. And now we can actually distribute this mod inside the integral. Integral over gamma of mod of natural log of z divided by mod of z squared plus 1 the whole thing squared times mod of dz. Now before going forward, there is this one nice triangle inequality that I would like to discuss and use. So this triangle inequality has many different alternate forms, but so one of it says, say if you have two complex numbers z1 plus z2, that's going to be less than mod of z1 plus mod of z2. So z1 plus z2 mod is less than z1 mod plus z2 mod. And if you want to consider negatives, so mod of z1 plus z2 is going to be greater than mod of z1 minus mod of z2. So when we have a negative, then the mod of the sum is always going to be greater, and compared to if we have a positive, then the sum of the mods is going to be greater. And the one that we're actually going to use is this mod of z squared plus 1 is going to be greater than or equal to mod of z1, z actually, we just have z, the whole thing squared minus 1. So we are going to apply this to this denominator. So, and there is another property, say if you have mod of z squared, this is nothing but mod of z but the whole thing squared. So we can apply that, and over here we can have mod of z squared plus 1 but the whole thing squared. And now since this is in this form, we can apply this inequality. So mod of z squared plus 1 the whole thing squared is going to be greater than or equal to z mod z squared minus 1 but the whole thing squared, because of there is this squared outside also. That's if they are on top in the numerator. But what if you have them in the denominator? So if you have 1 over mod of z squared plus 1 the whole thing squared, then you can flip the inequality to be less than or equal to 1 over mod of z the whole thing squared minus 1 the whole thing squared. So we are going to use this now and convert our denominator. So we will have, this is less than or equal to, well, we can actually drop the 2. There's no need, there's an inequality, right? So 2 times something is always going to be, actually, there's no point in keeping or dropping the 2. Just let's just let it be. So this, by this inequality we can write as is less than 2 times integral over gamma of absolute value of, or wait, mod of natural log of z. I don't know why I keep calling it absolute value, and then divided by basically mod of z squared minus 1 the whole thing squared, and we have a mod of a dz here. Fair enough. Now it's actually time to consider parameterizing this expression. So for parameterizing we need to know how gamma was, how the path gamma was. So gamma was this semicircular arc, right? And we can parameterize this by saying let z equal to, what's the radius of this thing? Well, the radius was r, right? Because this point was r, this point was negative r, and 0 was in the center. So z is equal to r times e to the itth power, and this e raised to it will help us basically rotate on the complex plane. And when we make that substitution, we still have to account for the mod of natural log of z. So if you take the natural log on both sides here, we have natural log of r plus natural log of e to the it. This will be natural log of z is equal to natural log of r plus it. Now let's take the mod of both of all of these things. So mod of natural log of z is going to be mod of natural log of r plus I times t, which is going to be less than or equal to, by our triangle inequality, natural log of r mod plus mod of I times t. And a mod for a variable like this is basically is basically calling forth the maximum value that the variable can take on the entire interval that it is defined on. So since t we parameterized to go from 0 to pi, 0 over here and pi when it ends here after rotating 180 degrees. So the maximum value that the mod of I times t can have is just pi. So this just becomes pi. So we have this expression basically equal to natural log of r in mod plus pi. So let's plug all of this in. So this is going to be less than or equal to 2 times integral from 0 to pi, because that's how we parameterize t. Our natural log, mod of natural log is going to be mod of natural log of r plus pi divided by, and in place of z we have r times e to the it. So mod of r times e to the it, the whole thing squared, minus 1 the whole thing squared, and then dz, we didn't calculate dz is differentiating this with ri times e to the it dt, and the mod of that, mod of dz is basically, well, is going to be, well, mod of r is just r, mod of I is 1, mod of e to the it is basically the unit vector, so that becomes 1, and dt is just the changing variable, so dt is again dt, so this becomes r dt. So now the mod of r times e to the it, well, e to the it mod is just going to be 1, mod of r is r, so we have basically equality with this expression. 2 times integral from 0 to pi of mod of natural log of r plus pi divided by r squared minus 1 the whole thing squared with an r dt here. And now this is actually a very important step. Well, first we can just drop the mod now, because r is always going to be some real value, so natural log of r is always going to be real, and mod of a real number is the real number itself. So 2 times integral from 0 to pi of natural log of r plus pi over r squared minus 1 the whole thing squared r dt. Now this is an important step. We have to take the limit as r goes to infinity. When we do that, you can see that the denominator is going really fast compared to the numerator, and we can establish that using L'Hopital's rule. So we have 2 times integral from 0 to pi of r natural log of r plus pi r over r squared minus 1 the whole thing squared dt. And when we take the limit as r goes to infinity, let's actually apply L'Hopital's rule if you want. We have 2 times integral from 0 to pi of r over r is 1 plus then you differentiate r, you just get natural log of r plus pi divided by 2 times r squared minus 1 times 2r, so we have 4r dt, again in the limit as r goes to infinity. And let's apply L'Hopital again, if you please. We have 2 times integral from 0 to pi of, all of these will go to 0, we have 1 over r divided by, this is 4 times r cubed minus r, so 4 times 3r squared minus 1 dt, so I'm not wrong. And then you can just take this r down, so we've dt over 4r times 3r squared minus 1 in the limit again as r goes to infinity. So the denominator is just blowing off to infinity, which makes the entire fraction go to 0. So this entire part of gamma, this entire thing, the absolute value is less than or equal to 0, right? Because there was always this less than or equal to inequality chain that was going on until this, which was 0. So this 2 times mod of something is less than or equal to 0. But if you have a mod, the expression, the modded expression can't be negative. Can't be negative. Because as I said, this is an extension of the absolute value for complex numbers. So if you have something less than or equal to 0 and you know it can't be less than 0, it has to equal 0, right? So this thing just entirely goes to 0. So the entire integral over gamma is 0. That's how the estimation lemma is useful for calculating these unwanted regions. So by estimation lemma, this just went to 0. And it's now time to move on to calculate what this entire contour integral is equal to using residue theorem, residue and poles. See you on the fresh page. So now this has a structure, f of z has a structure like this, and we can just bring the power down now. For calculating residues, having a natural log of z squared is harder to work with than 2 times natural log of z. So we just bring the 2 down. And notice that the poles are basically values where the denominator goes to 0. So this entire expression goes to 0, which means z squared plus 1 should equal 0, and that equals 0 when z is plus or minus I. So for plus I and minus I, but again we should concern ourselves with only those poles which are inside our contour. So our contour was something like this, from minus r to r, and I is just one unit on the imaginary axis, minus I is minus 1, or like in the negative y direction on the imaginary axis. So what's inside the contour? Well, positive I is. So we drop the negative, we drop this negative part of it. We're only concerned with the pole when z equals I. And notice the order of the pole. To find the order of the pole, we need to look at this power over here. So it has second order poles, and I'm going to write the general expression to calculate the residue for second order poles or nth order poles in general. So that's basically going to be residue is going to be 1 over n minus 1, the whole thing factorial, limit as z goes to that z naught, that value of the pole, and we have the n minus 1th derivative of z minus z naught to the nth power times our function that we had. So this is the general expression for an nth order, for a residue with poles of nth order. And so for n equals 2, this is going to look like 1 over 2 minus 1, or 1 factorial, times limit as z goes to basically the pole value I. This is the residue at z equals I of f of z of basically the first derivative. N minus 1 is 1, so the first derivative of, we can factorize this out. So wait, z minus I squared, and f of z is basically 2 we can take out of everything. 2 times the natural log of z divided, we can factorize the denominator as z minus I squared times z plus I squared. And the best part is, well, these cancel out nicely. So we have 2 over 1 factorial, which is 2 times limit as z goes to I of the first derivative of natural log of z divided by z plus I squared. So we'll have to use the quotient rule now for this. This is going to be basically 2 times limit as z goes to I of z plus I the whole thing squared divided by z minus 2 times natural log of z times z plus I divided by the square of this. So z plus I square is 4th power. Now when we plug everything in now, we have 2 times limit as z goes to I. Well, actually don't need to write the limit again. So we have, well, I plus I is 2I squared, or 4I squared, which is negative 4 divided by I minus 2 times natural log of I times 2I over here divided by 2I to the 4th power. 1 over I is just negative I in the numerator. So we have 2 times 4I minus, well, there we have a 4 here. We have a 4 here, so 4I, and then natural log of I can be written as e raised to I pi over 2. So the natural log of I is just I times pi over 2. We have I times pi over 2 here. Divided by 2 to the 4th is 16. I to the 4th is 1. Because I squared times I squared minus 1 squared is 1. So we have 1 over 8 over here. 4I, and we have negative I squared, which is going to be 1, plus 2 pi, which will simplify to basically this will simplify to I over 2 plus pi over 4, if I'm not wrong. That is the residue, and that was the only residue we needed to concern ourselves with. And we have this nice property in residue theorem that the contour integral of some function f of z dz on a closed contour that enclosing some residues is equal to 2 pi I times the sum of all the possible residues at various points that are placed inside the contour, basically all the poles that are inside the contour. We only had one pole at z equals I inside the contour, so the sum of residues is basically just residue at z equals I. So that's going to be 2 pi I times whatever we calculated, I over 2 plus pi over 4. That's going to be this negative, and the 2's will cancel out, so negative pi plus I times pi squared over 2. That's why, yeah. So that's the value of the contour integral entirely of f of z dz. Now let's go back and plug this into our contour equation. So now in place of this contour integral of f of z dz, we just have minus pi plus I times pi squared over 2. And since we took the limit over here for estimation lemma, let's take the limit again. So limit as r tends to infinity of integral from minus r to r of f of x dx, because it's on the real axis, is equal to minus pi plus I pi squared over 2. We can just apply the limit with integral from minus infinity to infinity of f of x dx is equal to minus pi plus I times pi squared over 2. And we can just substitute f of x. What was our f of x? It was just this, right? I. Integral from minus infinity to infinity of natural log of, in place of u, let's just write everything in terms of x squared divided by x squared plus 1 the whole thing squared dx. Let's check, yeah, that's right. Is equal to minus pi plus I pi squared over 2. But now, and here's an interesting observation, that this integral was entirely on the real axis, right? It was, if you look at the contour, this was on this axis entirely, what I'm marking with green. And by the Riemann sum definition, of an integral, that's like saying if you have, say, k equals 1 to infinity of some f of k and then some delta k, which is really small, in the limit as delta k goes to 0. That's the basic structure of Riemann sum. If you're having delta k's that are real, because they are on the real axis, right? So the only delta k's you'll have are delta x's, which will only be real. There will be no imaginary part in them. And this f will always take in a real variable, because again x is a real variable. So f of x is a function of a real variable. So this will always result in some real value, because in order for things to be complex, you need real part plus imaginary part. But that imaginary part won't be there, because this, by the Riemann sum definition, is always going to be taking real parts and inputting real x variables. So this will always result in a real value. That's why this will always have to be real, whatever this results in, and there will be no imaginary part to whatever value this is. And look at the right hand side, we have I times pi squared over 2. So this is the imaginary part actually. The pi squared over 2 is the imaginary part. So since this can only be real, this will only take on, it will ignore this integral, will ignore this imaginary part, and it will take on the only real value that it sees over here. Therefore, our I, which was defined as integral from minus infinity to infinity of natural log of x squared divided by x squared plus 1 the whole thing squared dx, is just equal to negative pi, because it can't take this imaginary value, because this is a real integral resulting in a real value. So that's a really neat answer, given all the trouble we went through. And I hope you understood well the entire process of contour integration and complex analysis. And finally, to conclude everything, we have I defined as integral from 0 to infinity originally as natural log of x divided by square root of x times x plus 1 the whole thing squared dx. And we used a contour integration residue theorem, which were parts of complex analysis, to get an answer of negative pi, excluding the imaginary part, because this is a real integral. It will always result in a real value, which is basically negative pi. So that's it for this video, guys. So please like, share and subscribe to my channel. Recommend me to your friends who are actually wanting to learn maths on their own during this period of crisis. You can follow me on Instagram. I have the username gamma_digamma. And in the meantime, stay home, stay safe, have a great day, and peace out.